Hello, NEET warriors. I hope I'm audible and visible. Welcome aboard to the Unacademy NEET English channel, and this is your physics educator, Captain Shreyas, going live in the second part of magnetism. And we are going to continue from the previous part, the lecture 1, which we had done last week. And I hope you have watched that lecture before. In case you haven't, please find it in the playlist of 12th standard or the Conquer batch, or in the past live section videos, right? In this particular session, what are we going to do? See, these were the things that we had done last lecture, the ones which are faded out. Today we are going to do magnetic field due to current carrying elements, the Biot-Savart Law. Then we will see the magnetic field due to different geometries, and then we'll go to Ampere's law, and then we will go to solenoid and toroid, which are some amazing applications of Ampere's law, and then we will also see the force between current carrying wires, right? So this is what we aim to do today, and after this lecture your entire magnetic sources and effects, you know, that entire unit is over. After this we'll go on to Earth's magnetism, magnetic properties and materials. That will be in the next week, right? So I hope you guys are all geared up and ready, and smash the like button out there. Hello Sarumati, hello Knowing, hello Nani, Subita, good evening Pravina, good evening Priyanka, good evening Dr. Asta, nice to see all of you. Hello Ritigna, hello new student, and Nani needed this batch, very good. So here you are on the NEET Conquer series, right? This is a full-fledged batch where I teach with full josh, full energy, and in this particular NEET Conquer batch that you are having on YouTube, you have the energized batch on the platform, by the way. So many students are already a part of it. So if you want, you can already, you might have joined, or you can join it. So I'm going to take care of all the chapters. I'm going to not only just do theory, but also problems, PYQs, everything that you need. So I can guarantee you, more than 170 marks in NEET physics next year. Just stay with me, because there will be a lot of random noise, around, and you might think that this is good or that is bad or what is it. So don't be confused, just keep following me properly, 100%. I will make sure that you will get 170 plus, right? So let's begin with the class, and let's start talking about magnetic field due to current carrying element and the Biot-Savart's law. Ready, my dear students? Okay. So long time back, Oersted was the guy who discovered that when you pass current in a wire, then magnetic needles get affected by it. Then he immediately concluded, well, when a wire carries current, it must have some kind of a magnetic field around it. So he saw that when you have, let's say for example, this is a wire which can carry current. If this current is present, then a needle placed around, then this particular needle which is placed around, that needle got basically deflected. It basically got deflected. And if the direction of the current was reversed, the current in this case, if it is basically, let's say, reversed, then he saw that the same needle at the same distance, the same needle at that same particular point, it also reversed its direction. So the deflection was on the other side. So the deflection also gets reversed. This particular experiment, just proves. This was Oersted's experiment. This was Oersted's experiment. What did Oersted's experiment say? That whenever you have a current carrying wire, that particular current carrying wire generates magnetic field around it. Remember, the symbol for magnetic field was B, and the unit for magnetic field was basically Tesla. Tesla is the SI unit of magnetic field. That's what he was able to conclude. And then he also saw that if that wire is carrying current like this, and you sprinkle some iron fillings on a cardboard sheet, maybe that cardboard sheet is, let's say, like this, those ion fillings align themselves when tapped in beautiful circles, okay, something like this. So the ion filings, right, arrange in basically concentric circles. Remember, ion fillings are magnetic materials. They are magnetic in nature. They get affected by magnetic fields. So because they arrange themselves in circular form, it was logically then concluded that the magnetic field around it is basically in the form of concentric circles around basically a straight wire, keep this in mind. So if this wire carries some current, then the magnetic field lines are in the form of concentric circles. Is this much part clear? Everybody with me on this? Awesome. Nani, concentrate on the class, don't deviate on the other things. Wherever I am doesn't matter, just concentrate on the class, right? Good evening, Akansha. Awesome. Oh my God, Alekia, it means a lot. You have shifted my tuition to attend the class. That shows your dedication, sincerity. Proud of you, bacha. It means that I have a lot of responsibility now. Cool. Now, Oersted told about all these things, but Biot-Savart gave a law to find the value, direction properly in vector form. So let's see what their law was. To understand their law, remember, your wire need not be straight always. It could be curved. Let's say, for example, the wire is bent in this particular form. This is some wire which carries current. This is some random wire carrying some kind of current. This wire is made up of small elements, and if I choose some random point, say for example over here, this is the point where I want to find the magnetic field, then what I do is I divide this wire into small elements. Each small element which carries some current, this is an element of that wire which carries some current. That element at this particular point, will create a small magnetic field. Like that, there will be so many elements. I would say, so many elements like that. Finite number of elements. Each element at that particular point, you will see will create a small magnetic field, because a small element will create a small magnetic field. So I would say the net magnetic field at that particular point is nothing but the integration, or basically the sum of the magnetic fields due to basically those elements. So essentially what I can say is that the total magnetic field is integration of the small magnetic fields due to each of those particular elements. So you integrates means addition. You have to take the sign, the direction, the magnitude, everything into account to find the resultant magnetic field. Is that making sense? Everyone with me? So each element creates a magnetic field, then I can get the total magnetic field by integrating or combining all their effects. Now the question obviously in your mind will be, how much is this small magnetic field? How much is that small dB? Because if I know dB, I can integrate to find B. So let's see that formula given by Biot-Savart. So this is how it looks like. Biot-Savart's law. You show some random wire, Okay, you show some, let's say, random wire which carries some current I, and at some location from an element you take a position vector. The position vector points towards the point where you want to find the magnetic field. Due to this small element, this is that element, the length of that element is dl. The dl element is also a vector. The direction is given by the direction of the current. So if the current goes like this, the dl, small element which generates the magnetic field here, is basically that is a vector quantity, and r is the position vector of that point. So I'll just mention it. dl is nothing but the element in basically the direction of the current. R is basically your position vector. R is basically your position vector where you want to find the field. Now first understand the direction, then I will go to the magnitude. First understand the direction, then I will go to the magnitude. Understand this. Always the direction, you can find it by taking the cross product, basically A cross B, using your right hand rule, go from A to B, okay, where the cross product is of dl with r. dl cross r gives you the direction of the magnetic field. Come on, everybody, use your right hand like this, point the four fingers in the direction of dl, slowly turn it towards r. Don't you see the thumb is going inside the plane of the board? dl, slowly turn it towards r. The thumb obviously goes this way, so hence the magnetic field must be inwards. Hence the magnetic field must be like a cross, so it is inside the plane. So this is your small magnetic field dB bar. Is that much part understood? Everybody with me on this? Is this part understood? All right. Okay. Board is not covered. Acha, we need to move the camera. Some part is not seen. Is that so? Let me just adjust again. Let me see once more. Okay, just see if it is fine now. I think earlier a part of the board was missing. Just see now if it is fine. Yep. Cool. Okay, so what is this dB given by? This dB, according to Biot-Savart's law, is given by, observe carefully, there is a constant called mu naught. I will explain you what that is, divided by 4 pi. All right. Then you have I dl, okay, and you do cross product with r bar, and then divide it with the magnitudes cube. So that becomes the Biot-Savart's law, which gives you the magnetic field due to a small element carrying current at some distance, at some position r. That's all. Now what are these terms? Don't worry, I will explain this to you. Some of you might be remembering electrostatics now, where we had seen electric field due to a charge is 1 by 4 pi epsilon naught q by r square. This looks very much similar, just that there is a cross product over here. You can see there is a cube term over here, but actually speaking, this r bar and one of the r gets cancelled. Strictly speaking, there is r square, because dl cross r will be dl r sine theta. 1 r from the top and below cancels, so still it is inverse square law. Inverse square means that the field is inversely proportional to the square of the distance. As you go far away, the field reduces, inversely proportional to the square of the distance. So although there is r cube, be careful that one of the r gets cancelled from the top. Okay, right now it is not cancelling. When you expand this, when you simplify it, definitely it will. What is this mu naught by 4 pi? First of all, let me tell you what is mu naught. Mu naught is basically the permeability. Just like you had permittivity. Permittivity decides how many field lines go through a dielectric medium. It tells you, how permissible are those electrical field lines in a particular medium. Similarly, permeability is for magnetism, for magnetic field lines. How easily those magnetic field lines can penetrate inside a particular medium. So that is given by permeability. So mu naught is the permeability. Mu naught is basically the permeability of free space, basically vacuum, of nothing but free space. And this value of mu naught by 4 pi is 10 to the power minus 7 SI units. Very important value, you should know this. Or mu naught is 4 pi into 10 to the power minus 7 SI units. So that is the value of permeability of vacuum. For other mediums it will be obviously different, and it will be given to you if the need arises. Otherwise, don't worry, you will just deal with air or vacuum. Cool? Everyone with me on this? Understood? Clear? Let me take some examples so that you are confident with the directions. You are confident with the directions. Come on, everybody, start doing this. Let's take a wire which carries some current I like this. Let's take a wire which carries current I, let's say like this. Okay, these are just some wires which carry current. Let's take a wire which carries current basically like this. Okay, which carries current like this. Okay, let's take some points. Let's say I take the point here, this green dot. Come on, think about it. Where will the magnetic field be? Where will the magnetic field be because of this element? This element is dl. I am at a distance of r, so r vector will be here. R vector will be here. So if you do dl cross r, do you see the thumb going inside? dl cross r, do you see the thumb going inside? Everybody with me? Everybody? dl cross r, the thumb goes inside. So hence the magnetic field must be inside the plane of the board. Inside the plane of the board. If you take, let's say, this element, and I say, listen, you have to take a point here. You have to take a point here. Okay, so come on, length is here, you are at a distance like this. This is the position vector. This is the position at which you are being placed. So if you do dl cross r, you will have to do little bit crazy stuff. dl is here, r is on the top. Come on guys, dl is here, so you will have to stand like this. You have to take your hand behind your head like this and do dl cross r. dl is this way, pointing towards your head, and then it is going on the top. You can see that the magnetic field is going inside in this particular case. You can see the magnetic field is going inside this, right? In this particular case, let's say for example, you take a point over, let's say maybe not just here, maybe you can just take it over here. All right, so this is now my position vector. This is now my position vector. Now I have to do dl cross r. The element is directed downwards, length is directed downwards, then do r, cross r. So take your right hand, put it like this, not like this. So imagine you take your palm like this, make it go like that. So length is downwards, slowly bring it up, slowly bring that length up. You will see the thumb coming behind you like this, meaning it is coming out of the plane of the board. So basically the magnetic field is coming towards you. This is how you can locate the direction of the magnetic field. Yup. Everyone with me? Similarly, if I just take a point on this side, believe me, the magnetic field will be exactly opposite. Here it will be towards you. If you take a point exactly opposite it, here the magnetic field will be again towards you. If you take a point exactly opposite, here the magnetic field will be inside. Do you know why this might be happening? Why on the other side the magnetic field direction is changing from in to out or from out to in? The reason is very simple. Understand, the magnetic field goes like that and comes out over here. It goes in like that. Imagine it's going behind and it is coming out. Or here also, it's going behind like this and it is coming out from here, right? Or here also you can think of it like that. It is going in like that and coming out basically from here. So you can imagine it is going in and it is coming out from behind. So that is why the direction flips. You can use your right hand, use L cross B rule, right hand rule, still you will get the same answer. But logically speaking, the magnetic field lines are going in circles. That's the reason why the direction is flipping over here. Okay, MBBS, I'll see to it later on, but first let's continue with this lecture. Okay, awesome. So probably we can start with some basic questions so that you get a hang of Biot-Savart's law. First question is up on your screen. There is a small element dl whose length is dx I cap, where dx is a small distance 1 centimeter. It is placed at the origin. You are allowing some current in it, which is 10 amperes. What is the field on the y-axis at 0.5 meters? Let's visualize if you want to. Okay, imagine our element which carries current is like this. This is that element. How much is the length? 1 centimeter, that means 10 to the power minus 2 meters. And how much current it is carrying? 10 amperes. I am on the y-axis. I am on the y-axis at a distance of 0.5 meters. So you basically go up by 0.5 meters on the y-axis. Okay, and at this point the question is, what is the magnetic field? Okay, let's just use our standard Biot-Savart's law. The magnetic field will be mu naught by 4 pi. Mu naught by 4 pi. Here you have IdL cross R divided by R cube. What is mu naught by 4 pi? It is 10 to the power minus 7 into. What is the current? It is basically 10. What is DL? DL is basically this distance but I cap. So it is basically 10 to the power minus 2 I cap cross R. What is R? R is the position. So it is basically 0.5 but in J cap direction. The whole thing you divided by R cube, basically 0.5's cube. Basically 0.5's cube. Everybody got it till this point? Everybody got it till this point? Understood? Clear? Now you can see some things get cancelled, like 0.5 and this 0.5 becomes square. Okay, now 0.5 is basically half. 0.5 is basically half. So it is basically half a square. When you do half a square, it will become 1/4. That 4 will go on the top. That 4 will go on the top. So might as well write 4. This half square will be 1/4, but it is in the denominator of the denominator. So it will go in the numerator. Okay, now take care of the powers of 10, then we will do I cross j. 10 to the power minus 7 into 10 will be 10 to the power minus 6, right? And this will become 10 to the power minus 8 again. So basically into 10 to the power minus 8. Okay, now last thing is I cross j. What is I vector cross j vector? It is basically k vector, k hat. Exactly. So it will be 4 into 10 to the power minus 8, and that would be k hat. Where is it? Okay, so basically that is nothing but option B. Okay, I think the option is not marked over here. Maybe the slide is not there, but yes, option B is the correct answer. Is that right? Very good, Pravina. Very good, Naveen. Excellente. Yup, Priyanka, it is k hat. Yes, you won. Yes, Alekhya. Awesomeness. Awesomeness. Keep it up. Keep it up. Let's go on to the next one. Let's go on to the next one coming up on your screen. The magnetic induction, basically magnetic field at a point which is at some distance from a wire, then the field at 12 centimeters will be how much? Okay. So over here, okay, to solve these kind of problems, what are we going to do? Think about it. Magnetic field at some distance r. For that we need a formula. So we will first talk about that formula and then we will come to this particular question. We right now know the magnetic field due to an element. We right now know the magnetic field basically due to an element. But due to a wire, it will be different because you have to add all the fields due to all the elements. So just imagine I have a straight wire, okay, and I am at some distance. I'm at some distance r from it. Then this wire which carries some current, will create magnetic field around it, something like this, concentric circles. This is how the magnetic field will look like. So at this point the field is going in and from there it is coming out. It is going in and it is coming out. And you can see why that should happen. You can use again your right hand rule. Place the thumb in the direction of the current. The magnetic field lines go around it in circular arcs. or circles, concentric circles, as directed by your four fingers. Those four fingers of your right hand will direct how those magnetic field lines should go. So hence the magnetic field over here should be inside. Magnetic field over here should be inside. But how much is that field can be given by a general formula. I'm going to give you the God formula and then we can see some modifications in it. So what is that God formula? Observe. Imagine this wire is not infinitely long. Maybe it is just a finite wire. You take this point, you take this point, and just imagine two lines, okay, starting from the endpoints to the point where you want to find the field. Then mark this angle, let's say I call it alpha, mark this angle, let's say I call it beta. These are the angles subtended by the endpoints. Then the field at that point, which happens to be integration of dB. So when you integrate it with proper limits, derivation is not important here. Just look at the formula and the application. So no need to study those derivations for NEET syllabus. Remember that. The formula which comes out is something like this. Mu naught by 4 pi. Here you have I by basically R, and you have over here sine of alpha plus sine of beta. This becomes the formula. This becomes the formula of the magnetic field due to a long wire, not an element, it's a long wire. First things to notice, there is magnetic field which is inversely proportional to R. Mu naught by 4 pi is a constant. Magnetic field is proportional to the current. That means if you pass more current, field increases. It is inversely proportional to R, meaning if you go away from it, the field reduces. Sine alpha and sine beta terms are there to accommodate how large this wire is. If alpha and beta are different, you will see the field over here will change. Larger the wire, more will be the field. Smaller the wire, alpha and beta will automatically reduce. It will change the magnetic field. Is that right? Everybody with me? So how much is this field is given by this particular formula. How to use it? I will show you. How to use it? I will show you. Observe. Imagine you have an infinitely long wire. Okay, you have an infinitely long wire. What is this? Infinitely long wire. This is infinitely long wire. So if you have an infinitely long wire and I am standing at a distance of R from it, the current in it is I, then the magnetic field at this particular point, because the current is going on the top, hold your thumb in the upward direction, the fingers go round and round like this, the field is going inside like this. So this is the magnetic field. That magnetic field will be given by mu naught by 4 pi, and what do we have over here? I and R, and here we have sine of alpha plus sine of beta. Now what are those sine alpha and sine beta? Let's talk about that. What is that sine alpha and sine beta? Alpha and beta are the angles subtended by the endpoints. So locate the endpoints. Where are the endpoints in this particular case? Can you visualize? The endpoint is at infinity. The endpoint is at basically infinity. This is at minus infinity, this is at plus infinity. So that means how much will this angle be? This angle alpha, won't it become almost 90? Won't this angle beta almost become 90 degree on this side? So what are those angles? Technically speaking, it is sine 90 and sine 90. And what is the value of sine 90? Everybody knows. Sine 90 is 1. Sine 90 is 1. Everybody with me on this? Sine 90 is nothing but 1. Exactly. So this will just become mu naught divided by 4 pi I sine 90 plus sine 90, which is basically 1 plus 1, which is 2, divided by R. So hence it becomes mu naught I divided by 2 pi R. So that is the magnetic field. There could be a problem where there is a semi-infinite wire. Semi-infinite wire. So what is this semi-infinite wire? Imagine the wire is long, yes, but on one side, on this side it is not long, it's just starting from this point, and there is some current in it, and I am standing at some distance r from it over here. So the magnetic field, will be given by, first locate the endpoints, so that I know the value of alpha and beta. This endpoint, because it is infinite only on one side, that is why the word semi, half infinity, infinite only on one side, not both sides. The first endpoint is over here, so you can see basically this alpha will be basically 90 degree. This alpha will be basically tending towards 90. Can you think and tell me what must be the value of beta in this particular problem? What might be the value of beta in this particular situation? The second endpoint is over here only. Do you see this is beta? Basically beta is nothing but 0. This beta angle is nothing but 0. How many of you saw that? Exactly. Because if you compare it with this diagram, it becomes very easy. If you take this point here, beta reduces and finally becomes 0. So hence beta is basically 0 here, and the magnetic field will be given by mu naught I by 4 pi r. Here you have sine 90 plus sine of 0. Sine 0 is 0, sine 90 is 1. So it will just become mu naught I by 4 pi r. Basically this one is half of this. This was, if it is mu naught I by 2 pi r, you multiply this with half, you get this. So it makes sense because this is semi-infinite, so it should be half of this formula. So if you know this formula for a long wire, for a semi-infinite wire, it will be exactly half of it. Everybody with me on this? Understood? Clear? Pakka? Okay. One more thing before we go ahead. If you are given any wire now, you can immediately predict the magnetic field's direction by using your right hand rule. Always put your thumb in the direction of the current. The four fingers will curl in a peculiar manner. So if it is curling in this way, that means the magnetic field lines are going like this. Magnetic field lines are basically going like this. So over here the magnetic field is inwards, over here the magnetic field is towards you. Similarly, if a wire is carrying current only like this inside the plane of the board, take your thumb, put it in the direction of the current, the four fingers will turn like this, So in this case, the magnetic field will be in the clockwise direction. In this case, it is basically in the clockwise direction. But if the current is coming towards you, take the thumb, put it in the direction of the current. The thumb should come out of the plane. The four fingers go like this. Hence, the magnetic field will be in the anti-clockwise direction. Right? It will be in the anti-clockwise direction. Understood how to get the direction of the field? Always thumb means current. And your four fingers of the right hand, the four fingers which basically curl, that is basically the magnetic field. This is nothing but your right hand thumb rule for long wires, for straight wires. Very easy. Okay, these are the tricks which will be very useful rather than using cross product and A cross B, which is very confusing at times. So what and all have we learned till now? We have seen that what is Biot-Savart's law and how you can, extend it to long wires, subtending certain angles. Using this formula, you can find the magnetic field. So from this, we found special cases like infinitely long wire and semi-infinitely long wire. So I think now it's a good time to start solving questions. Look at this. The magnetic field at a point which is at 4 centimeters from a wire is this much. Then what is the field at a distance of 12 centimeters from that same particular wire? So imagine you have a wire which carries some current. In the first situation, you are at a distance of 4 centimeters. In the second situation, you are at a distance of 12 centimeters. So what is changing? Basically, R is changing and we all know magnetic field is inversely proportional to R. You take any formula of long wire, it is something like this, mu naught by 4 pi, right, I by R. Here you have sine of alpha plus sine of beta. So it is basically inversely proportional to R. So if I take B2 by B1, it will be R1 by R2. That means magnetic field second time by original magnetic field, which was 10 to the power minus 3, will be first distance, which was 4 centimeter, upon second distance, which was 12 centimeters. 4 goes with 12 3 times. 4 goes with 12 3 times. So it will be 1/3 of 10 to the power minus 3. So it will be basically 1/3 of 10 to the power minus 3, but 1/3 is 0.33. So 0.33 into 10 to the power minus 3 Tesla, which is 3.3 into 10 to the power minus 4 Tesla, which is option A. And let's see how many of you got it. Very good, Priyanka Jinendra. Awesomeness. Proud of all of you. Great. So magnetic field will reduce because distance has become 3 times. So the field will reduce 3 times. Distance increased 3 times. So field reduced 3 times because it is inversely related to it. It was inversely related to it. Moving on to the next question on your screen. Come on. This you should be able to get it. Magnetic field due to a small element at a distance r is. All the formulas look confusing, but only one of them is correct. This is just to mix and match and play with your mind. That's all. If you're smart enough, you can get the answer very easily. You should know the formula. You cannot make any mistakes. Come on. Only one of the formulas is correct. One of them is Biot-Savart Law. Okay. Many people are saying D. Is that right? Well, oops, I think. Oh, the previous answer has come over here. Yes, it is D. It is D. Definitely. Obviously, mu naught by 4 pi I dl cross r divided by r cube. Remember, I had told you there is a cube in the Biot-Savart Law. So keep that in mind. Okay. Very good. Very good. Proud of all of you. Let's see if you can solve this NEET 2021 question. Wow, what a fabulous question. Look at this. Big question. Current is 5 amperes. This is a long wire. Look at this. Infinitely long wire in the x-axis. 5 amperes of current. It will create its magnetic field. That magnetic field at this distance will apply a force on the electron, which is moving. So there are 2 chapters combined, or 2 units combined, or 2 concepts combined. One is you have to find the field due to a long wire. Second, on a moving charge there is a force given by QV cross B. Do you remember that? QV cross B is the force on a moving charge. So that is the second concept. So that is asked in NEET. So let's see how many of you can find this out. First of all, you are obviously going to find the field. The field will be given by mu naught by 2 pi, and here you have I by R for an infinitely long wire. For an infinitely long wire which carries some current. So mu naught by 2 pi, I can write it as 4 pi into 10 to the power minus 7, that's the value of mu naught, divided by 2 pi into current is basically 5 amperes, divided by the distance, which is 0.2 meters, which is basically 0.2 meters. Okay, 4 pi by 2 pi is 2. 4 pi by 2 pi is basically 2. 2 and 0.2. 2 and 0.2 cancel and they will give you 10. So that will be nothing but 10 into 10 to the power minus 7 into 5. So that is 5 into 10 to the power minus 6, but Teslas. So that is the magnetic field. Okay. Now because of that magnetic field, the current is going like this. The magnetic field will come towards you. There will be a force. There will be a force, and that force is given by Q V cross B. Basically, it will be Q V B. In this case, it is sine 90. So why is it sine 90? Because magnetic field is towards you. Velocity is this way. Angle between magnetic field and velocity, you can see angle between them is basically 90 degrees. Both are at 90 degrees. Okay. So what is the charge? It's an electron, right? I think it's given. Yeah, so it is going to be 1.6 10 to the power minus 19. Perfect. What is the velocity? It is 10 to the power 5. What is the magnetic field? 5 into 10 to the power minus 6. Okay. So look at this now. What happens? 1.6 into 5. 1.6 into 5. 16 5s are basically 80. So this will just become 8. Right? And over here, 10 to the power minus 19 and 10 to the power minus 6 will make it 10 to the power minus 25. So plus 10 to the power 5 plus 10 to the power 5 will make it 10 to the power minus 20. So that many newtons should be the answer. 8 into 10 to the power minus 20, which is option B, of course. What a question. Did you love it? Understood? Simple calculations. I am taking it very slow. Obviously in the exam, if we have to do it, we'll do it tuck 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 tuck. Okay, I will not be explaining, right? So obviously the way in which you solve in the exam, the speed will be very different than the way we will learn, and that is something which you should always keep in mind. Very good, Namuta, Priyanka. Awesomeness, awesomeness, awesomeness. Let's go on to the next question coming up on your screen. What do we have? Look at this. Two semi-infinite wires. So this is one point. Next point is at infinity over here. This continues, okay? This is till infinity like this. These are semi-infinite wires parallel to each other. Distance is 2D. So this total distance is 2D, and this point is, I think, exactly in between. Yes. So from here to here is D. From here to here is also D. Okay. Magnetic field is 0 when the currents are parallel or anti-parallel, and it is not 0 when parallel or anti-parallel, basically same direction or opposite direction. So you have to fill in the blanks. Remember, filling the blank questions are quite likely in the NEET examination. So there could be new pattern of questions as well. Okay, think about it. Think about it. Both these wires are there. Each wire will create its own field, yes or no? Each wire will create its own field, yes or no? Okay. So think, imagine if, say for example, this wire is carrying current like this. This wire is carrying current like this. How will the field because of this wire will be? Take your thumb. What did I tell you? Take your thumb in the direction of the current. Automatically the four fingers will go in the direction of the field. So the field is going inside and coming outside. Going inside, coming outside. So it is going in at that point P. So it is going like this. It is going like this. Correct? Everybody with me? Pakka? Okay. Assume now the currents are in the same direction. Assume now the currents are in the same direction. So let's probably take this current like this. Again, take your thumb, put it in the direction of the current. See how the curled fingers are going. Goes in from there, comes out from here. Goes in from there, comes out from here. So it is coming out from here. That means it is towards you. That means it is towards you. Everybody with me? Perfect. Now do you see both of them? What is happening over here? Both of them are basically cancelling out each other. So both the fields are opposite, equal and opposite, because distances are same. So net field will be 0. So the net field is 0 when the currents are essentially in the same direction. In the same direction, or basically parallel to each other. Very good. So naturally this will be opposite, but still if you want to see, observe. Imagine the current to be like this. Take the other current to be like this. Take the other current to be like this. Because of this yellow guy, the field will be obviously still like this only inside. But because of this current, take your finger of the thumb basically downwards. The curled fingers are like that. They go from there and go in. They go in on this side. So basically it is going in like this. So they are basically not cancelling. In this case, they are adding up. They are adding up. Yep. So it is, the second answer will be in opposite direction. It will not be 0. The first question said 0. So 0 when same, non-zero when opposite. That's how you conclude. Cool. Let's go to the next question coming up on your screen. Now, to solve this question, okay, you might need a special case. Okay, I want you guys only to think about it, but still, if you're not able to think about that special thing which will be needed, it's okay, I will be letting you know. Look at this. This is a wire which is bent infinitely long on y-axis, infinitely long on the x-axis. Current comes from positive x, goes to origin and goes to positive I till infinity. Comes from here and goes here. Comes from there and goes here. That's how the current is flowing. Okay. Now because of this part and this part, there will be some magnetic field at this point, which is at 0 coordinate in x and negative a coordinate in y. Question is, how much is the magnetic field? The net magnetic field. Obviously, even this part and this part, they will have some magnetic field individually. So I have to add their magnetic fields to find the net magnetic field. So think about it. How much will be their contribution? How much will be their contribution? Okay. Let's start with this y-axis wire. Let's start with the y-axis wire. Okay. Now, you might be wondering, okay, this y-axis wire is carrying some current. How much will be the contribution? If I remember Biot-Savart's law correctly, if I have a current carrying element like this and by chance I take r vector here, or if I take r vector here, what happens, you know? dl cross r will be a big fat 0. dl cross r will be a 0 because sine of 0, or if you take sine of 180, both of them are 0. Sine 0 or sine 180, both are 0. dl and r in the same direction, sine 0, 0. dl and r opposite direction, 180 degree, that is also 0. That means on the axis of the wire, what does this tell you? On the axis of the wire, the field is 0. On the axis. If you go away from it, yes, it is there. If you are on the wire, extended part of the wire, the field is 0. That means if you take this particular wire, my dear warriors, isn't this point on the extension of the wire? Isn't this point on the extension of the wire? Basically, the axis of the wire will have no field. So this wire is not even contributing. This wire is definitely not contributing. Do you understand this? So this part has no contribution. So there is no contribution. There is no contribution. So now it is just like only this particular wire is there. Only this wire is there. And only this much wire which is carrying some current. This is like your normal semi-infinite wire which carries current. And what did I tell you? The magnetic field due to a semi-infinite wire is half of that of the infinite wire. So mu naught by 2 pi into I by r. R over here is basically this distance. So that r is nothing but a, because the coordinate of that point is given to be a. So you will just put a over here. So that will also be the total magnetic field, because this guy has no contribution in it. So it will be mu naught I by 4 pi into a. Is that right, my dear warriors? Exactly, Alekia, perfect. And if you ask about the direction, well, the current is going like this. The current is going like this. The field will go inside from the top and will come outside from below. So at this point, the magnetic field will be towards you. The magnetic field will be towards you in the k cap direction. So that means the total magnetic field will be mu naught I by 4 pi a, and this will be k hat if vector form is asked. But otherwise you can just leave it as outwards or just the magnitude. Very good, excellent. Moving on to the next question coming up on your screen. Find the magnetic field at the center of a coil having side A and current I. Wow, we have a square coil and the question is, find the magnetic field at the center of this particular square coil. First of all, a square is made of 4 sides. Each side is like a wire which carries current. Okay, that is your hint now. If each side is like a current carrying element, so I can find the magnetic field at this point due to each of those sides and just multiply it by 4. Makes sense? You find due to this how much it is, due to this will be same, because it's a square, same current, same distance, nothing will change. So you just multiply it by 4. Yes or no? Okay, so that is something which is there in my mind. Why not just take one of the side, treat it like a finite wire which carries some current I. The side length is totally a, correct? You are standing at a distance of a by 2 if I am not wrong. Why is this a by 2? Because the total side length is a. Please keep this in mind. the total side length, this whole thing is basically A. So this will be A by 2. What did I tell you? Always locate the endpoints. This is first endpoint, this is second endpoint. Join the endpoints to the point where you want to find the field. Join the endpoints where you want to find the field. This will be alpha, this will be beta. Can you guess the value of alpha and beta? Because this is a square, it might be little easier. Can you guess the value of alpha and beta because it's a square? Think about it, these are diagonals at the end of the day. This is a perpendicular over here, perpendicular over here. Obviously this is 90 totally, this is 45 and this is 45, right? This is like an isosceles triangle, this is a right angle triangle, right? Everything is like isosceles. So this should be 45 degrees. This should be also 45 degrees. Does that make sense? Yes, both of them are 45 degrees. Perfecto. Next important thing, I will find the magnetic field due to that part. So magnetic field due to the side will be mu naught by 4 pi. Current is I. Distance is not A, it is A by 2. Be careful. Into sine 45 plus sine beta, which is again 45. Okay. Sine 45 we all know is 1 by root 2. We all know it is 1 by root 2. Okay. So let's see what happens next. So mu naught I. This 2 and 4 cancels. It will become 2 pi A. Okay. Perfect. Sine 45 both 1 by root 2. So it will become 2 times of 1 by root 2. 2 and 2 cancels. So I am just left with mu naught I divided by root 2 pi A. Just check this out. Root 2 cancels. Root 2 pi A. That is the field due to one side. But that is not the final answer. Don't be happy over this point. The total magnetic field due to the square will be 4 times the magnetic field due to any one of the side. So it will be 4 times of mu naught I by root 2 pi A. If you want to rationalize it, it is perfectly fine. So mu naught I root 2 into root 2. Okay, so you just do root 2 into root 2, it is basically 2, and you have pi and you have A and you multiply it also by root 2. 4 by 2 is 2, so it will just become 2 root 2 mu naught, alright, divided by pi, and you have I divided by A. So that is the total magnetic field due to the square. That's the answer. Exactly. Very good, Alikya, Jinendra, Priyanka. Very good. Yes, Vedanjani, that was 45 degree. Yes, Dr. Asta. Awesome, awesome. Great. Let's go to the next concept, and that is basically magnetic field due to an circular loop. Till now, whatever problems we did, they were on straight wires. All the wires were straight, or maybe they were short, but they were straight. And we saw the direction, we found the magnitude, everything. So these are the common set of questions which you can get on straight wires. So we are going to solve all the geometries today, just like I promised. Let's talk about circular. First, let's visualize how a circular coil's magnetic field will look like. If you take a circle like this, carrying some current, let's say in this particular manner, there is some current I in this. The magnetic field lines look somewhat like this. Observe carefully now. Observe carefully. It will go like that. Something like this. This is how the magnetic field lines look like. Such a beautiful diagram, right? Such a beautiful diagram, right? Wow. But you might be wondering, sir, where are the arrow marks? Well, I'll tell you. In this case, the current carrying wire will be your curled fingers. Will be your curled 4 fingers. Remember that. The current, because the current is curved, no? So whichever turns will be the 4 curled fingers. So how are the 4 fingers curling? Like this. The thumb will give you the direction of the field. The thumb will basically give you the direction of the field. It is exactly opposite for a straight wire. If you remember, I just told you, for a straight wire, where did it go? Right over here. Right over here, maybe. Yes, the thumb was the current in case of a straight wire, not the field, and the curled fingers were the field. So it is exactly opposite over here. Okay, so that is number one thing that you should know. Now this is basically the axis. So this is how the field will look like, because the thumb will go outwards. So this is how the magnetic field lines must look. So better to show the arrow marks. Great. And this is basically the axis. This whole thing, this is basically the axis of the coil. This is basically the axis of the coil which carries current. Keep this in mind. Right? Everybody with me? Great. Now, how much is the magnetic field on the axis of the coil? Well, that requires a very interesting derivation. Maybe we can have a look at the derivation, because sometimes it could be asked in boards also. So the derivation goes something like this. First, let's draw a circle. This is your coil which carries current, and let's say this is the axis, and let's say this is the radius. Okay, I hope you are able to visualize. Now what happens is, on that particular wire, circular coil which carries some current, each element will give some magnetic field at this point. Let's say the distance, I will call it as x. Let's say the radius of the loop, I will just call it as r. Each point will give some magnetic field here. So the total magnetic field is the addition of all of them. So how to go about it is basically take a small element of current, or take a small element of current over here. Okay, there is a small element of current over here. This is dl. If you actually think about it, dl is coming towards you. If you actually think about it, dl is actually coming towards you. So if dl is coming towards you, at that particular point, if you want to find the field, that means this will be your position vector. This will be your position vector to find the magnetic field at this point, which is situated at a distance of x from the center. Just try to do dl cross r and think which approximate direction does the magnetic field come out to be. Because of this element which is carrying the current towards you, it is going like that, coming like this, going like that, coming like this. So it is right now coming towards you. R is like that. When you do dl cross r, dl is like that, dl is towards you, cross r, the thumb goes in this particular direction. So my belief is that the magnetic field will be in this particular direction. See if this makes sense. Everybody with me? Understood? Pakka? Clear? Now, if, for example, I take this angle, I take this particular angle as theta. If I take this particular angle as theta, and if I drop this as the perpendicular, and then obviously this is 90 degree, then what happens is this particular angle will now become 90 minus theta, right? If this is theta, this is 90 minus theta. Obviously then this angle will again become theta over here, and that next angle will become 90 minus theta. Every alternate angle will be theta, and every alternate angle on the other side will be 90 minus theta, right? That's how it is. This dB will now have two components. One component this way, okay, one component basically like this, that would be dB cos theta, and the other component would be like this. Which is basically dB sin theta. This is adjacent, so cos, this is far away, that means it will be sin. This entire analysis is because of this small element. But there are many such elements like that. There are many such elements like that, understood? Each element will give a similar magnetic field. Think about it. If I take all the elements, then what you will see is each element will give a similar magnetic field. One here, okay, one here, one here, one here, like that. In all the possible directions, you rotate it in 360 degrees, what you will see is something like a cone. Something like a cone, believe me. So something like this, something like this. See this. Are you able to visualize? You will get a cone-like structure if you take all those yellow lines which are being formed because of each of those current carrying elements. You take one element here, one element here, one element here, one element here, like that. If you rotate it throughout that loop, you will see one magnetic field will be there, one magnetic field will be here, one will be here, one will be here, one will be here, one will be here. So every dB vector is on the surface of a cone. Are you able to visualize this? Are you able to visualize this? Pakka? So that means what? That means what? All these magnetic fields together will produce a resultant. Will produce a resultant in this direction. Will produce a resultant in this direction. Why? Because all these components, Y components will get cancelled. Think about it. If this field creates this component, some field will create this component, they will all cancel. They will all cancel. Everybody agrees to this? Awesome. So I can just say that the total magnetic field is integration of not dB cos but dB sin theta. So it is integration of nothing but dB sin theta. This is on the axis of the coil. Now what is dB? dB is the magnetic field at this point due to this element. At this point due to this element. So that will be given by mu naught by 4 pi. Here you will have current and divided by, okay, dl is dl only, okay, let's keep it like that, into r, r is this small r, into sin theta. Sin will be, understand, angle between r vector and dl vector. dl is towards you, r is like that. Visualize, dl is like this, r is like that. The angle between them is not theta, it is 90 degree. Just visualize that. dl is towards you, r is like this. So if you visualize it in the horizontal plane also, you will see it is 90 degree. So actually r has gone down. Instead of being here, it has gone down. So it is 90 degree between them. So actually you should put sine of 90, not theta. That is one common mistake. Divided by the distance square, that means basically, distance cube, that is basically r cube. One of the r gets cancelled, and then you can also take mu naught by 4 pi outside. Mu naught by 4 pi outside, even with I you can take it outside. What you are left with is dl by basically r square. But let me tell you, r is also a constant. If you take this element or this element or this element, all these lines are the same. This is the same. They are all the hypotenuse. So technically speaking, I can even shift this r square outside. And what I'm left with is just integral of dl. Sin 90 was anyways 1. What is integral of dl? What is integral of dl? dl plus dl plus dl plus dl is the total perimeter, which is nothing but 2 pi r. So mu naught by 4 pi, here you have r square, and here you have just basically 2 pi and r. Is that right? Everybody with me? Everybody with me? Cool? Understood till this point? Understood till this point? And yes, that sine theta which was there, I will have to still put it, this sine theta, okay, this sine theta was always there. So that sine theta I missed, so I'm just adding it over here. This sine theta can also be further written down as, sine theta is opposite side by hypotenuse. So why not write sine theta as opposite side, which is r, divided by that small r. So basically 2 pi, 4 pi cancel. So mu naught I by 2 r square, and this r is as it is, and sine theta is nothing but r by small r. So this will just become mu naught I r square divided by 2 r cube. Mu naught I r square divided by 2 r cube. Last step. What is this small r? If you notice, what is this small r? It is nothing but r square plus x square whole raised to half by Pythagoras theorem. By Pythagoras theorem. Root of r square plus x square. So put it over here and you will get the final answer. So that will be mu naught I r square divided by 2. Here you have r square plus x square raised to 3 by 2. That is the magnetic field on the axis. And this is something which you should know. Okay, you should know about this. Just to summarize what we have done, I'll just summarize whatever we have done. We took a ring, we took small elements, each element created magnetic fields. Those magnetic fields look like this, like a cone. Each field had two components, one this way, one that way. These components will just cancel, only these components add. So by geometry I found that this angle is theta. So it is the dB sine theta of every dB that you have will add up to give you the total magnetic field along the axis. So we just said it is integration of dB sine theta, rest all was just substitution. Like sine theta you can see is opposite by hypotenuse, so capital R by small r. And you have to be very careful while integrating what is constant, what is not constant. That's all. Is that right? Everybody with me? This derivation can come in your boards. But for NEET perspective, even if you don't know the derivation, it's perfectly okay. So if you're a dropper, if you just remember this formula, more than enough. So mu naught I r square by 2 r square plus x square whole raised to 3 by 2. Remember this formula. Now tell me, if I have a coil which carries some current and I am exactly at the center, what might be the magnetic field? What might be the magnetic field at the center of a coil? What might be the magnetic field at the center of this particular coil? Think about it. When you go at the center, that means you are still on the axis only. You are still on the axis, but you have made x as 0. You have just made x as 0. That's it. So basically x is equal to 0. So if you use that formula also, what will you get? What will you get? Think about it. Mu naught I r square divided by 2. Here you have r square plus 0 square raised to 3 by 2, which is nothing but mu naught I r square divided by 2. This will become r raised to 2 raised to 3 by 2, which is r cube, because 2 and this 2 will get cancelled. Okay, r square and r square will get cancelled, 1 r will remain. So mu naught I by 2r. That's it. That's the answer for the magnetic field at the center when x is basically 0. Mu naught I by 2r. There is no pi here. There is no pi over here. Also keep in mind, if by chance this particular coil had many turns, this particular coil, let's say, had n number of turns, then the only thing that you do is multiply this with n. If the turns is 1, then n is 1. There is no doubt about it, you will not put anything. But if it has 5 turns, 6 turns, 7 turns, etc., then you will put that number over here. So that's how the formula is for the magnetic field at the center of the coil. Magnetic field at the center of the coil, right? This was on the axis of the coil. There is one more formula, although it is the same thing, just modified, but it can be useful. Like for example, imagine it's not even a complete coil. Imagine it's not even a complete coil. Imagine it's something like this. Maybe it just subtends certain angle theta, it carries some current. And I want to find how much will be the magnetic field because of that. How much will be the magnetic field because of that? How do I do that question? Well, if it's one complete turn, it's mu naught I by 2r. If it's 2 turns, it is mu naught I by 2r into 2, 3 turns into 3, 4 turns into 4. So if it is not a complete turn, maybe it is half a turn, maybe it is 1/4 of a turn, it will be a fraction, right? It will be a fraction. Everybody gets this? Everybody gets this? It won't be a complete whole number, whatever you write over here. If it is exactly, let's say it is a semicircle, that means this n would be half. If it's a quarter circle, that means that n will be 1/4, because it's not a complete turn. Understood? Hello, Hari Har Surdan, Gopika. To start physics preparation, where to start? I would say start from my first lecture of your NEET Conquer. That's it. Just start from there and you will catch up after some time. But start from the first lecture. That is the thing I would say. Right? Okay. If this much point is clear, then if this is angle theta, how much part? What is the fraction of the circle? What is the fraction of that particular coil which is creating this field? Obviously it will be theta by 2 pi. If this theta was 2 pi, it will be 1 turn. If that theta was 180 degree, it will be half a turn. So that is that fraction. That's it. So shouldn't the magnetic field formula be mu naught I by 2r multiplied by that particular fraction? That's it. That is the answer. So if you want, you can just rewrite it as mu naught I theta by 2r into 2 pi. So you can also write it as mu naught by 4 pi I theta divided by r. That's all. So that becomes the formula if it is not a complete circle, if it is an arc. Yes, this is the last lecture of this particular chapter. After this, we'll go to the bar magnetism, Earth's magnetism and all of that. Perfect. So, what and all formulas have we seen till now? On the axis, this is the formula, mu naught I r square by 2 r square plus x square raised to 3 by 2. This is how the magnetic field looks like due to a coil carrying current. But if it has to be found at the center, then you substitute x as 0, you get this formula, mu naught I by 2r. If there are more turns, you multiply it by n. If it's half a turn, 1/4, 1/6, 1/12, whatever turns, then you multiply it with that particular fraction. That's all. That's how you get the magnetic field due to an arc. Cool? So maybe we can start looking at some questions so that you get an idea. Okay, here is the question. A circular loop is kept in a vertical plane which contains the north-south direction. It carries a current that is towards the north at the top point, and A and B are the points east and west of it. The magnetic field due to the loop is, I would suggest to draw the diagram first, visualize it. Circular loop is kept in a vertical plane such that it contains north and south. So imagine whatever is front of you is north, whatever is behind you is south, right side is east, left side is west. Just imagine it like that. That will be easier. So this is your coil. Okay, this is, let's say, your coil. And if I had to show the axis, this is basically your east, that is basically your west, this is basically your up, right? This is your upward direction, this is basically your downward direction, this is basically your north direction, and same thing like this, this is your south direction. See if you are able to visualize this. The coil is in the vertical plane in the north-south direction. Perfect. It carries a current that is towards north at the top point. The current at the top point is towards the north. That means at this point the arrow mark of the current will be here. Naturally at the bottom point it will be towards the south direction. So that's how the current is going. Once I know the current, I can use my right hand's 4 fingers, turn it in the direction of the current, the thumb automatically goes towards the left side. That means the magnetic field because of that will be like this. The magnetic field will be basically like this. The magnetic field will come from here, go there. Come from here, go there. So the magnetic field is towards the west. Yep. So the question is the magnetic field due to the loop on both the points. One point is at, on the what? To the east of it. So one point A is here and the other point B is here. So obviously for both the points it is towards the west side only. So it is towards the west for both A and B. That is the correct answer. You can see this is west direction, this is also west direction. Perfect. Yep, answer D. Yes, Alekhya, correct too. Understood? Clear? Let's go to the next question coming up on your screen. If there is a circular coil which is carrying current, radius r, distance from the center where the field will be 1/8 that of the center of the coil. Understand this question? You have a coil which carries current. There is obviously some magnetic field at the center, but there also exists a point, I don't know where it is, where the magnetic field at that particular point is 1/8 the magnetic field at the center. Question is, find that point, find that distance. That's the question. Where is the magnetic field 1/8? I think it's all about substituting the formulas. Magnetic field at any point, which is obviously the point on the axis, is given by this formula, mu naught I r square divided by 2 r square plus x square raised to 3 by 2 is equal to 1/8. Magnetic field at the center is just given by mu naught I by 2r. That's the formula. I think many things will get cancelled, like mu naught I, 2 and this 2. That's it. Perfect. Take these people on the top, take these two people on the top on the other side. See what happens. So if you take it on the other side, it will just become 8r cube. 8r into r square is r cube. Take these people over here, so it will become r square plus x square raised to 3 by 2. Both have cube terms. Take cube root on both sides. So 8's cube root is 2, r cube's cube root is r. This guy's cube root will be just r square plus x square raised to half. Now square both sides, because this is power half. So to eliminate that half for square both sides. So this will become 4r square is r square plus x square. So therefore x square will be 4r square minus r square, which is nothing but 3r square. Now again take root. So x will be nothing but root 3 times of r. Root 3 times of r is just there over here. So the best part about this question is that you have to take cube root, cube, whatever, square root multiple times. So it's a bit of, algebra. Chances of silly mistakes are there. You might mess up the terms, you might get something weird if you make a silly mistake. So you have to be very careful while taking cube roots, squares, whatever. Okay, so that's a beautiful question. Just substituted the formulas for magnetic field at the center and magnetic field on the axis. Rest everything is basic algebra of handling the powers. Cool? Okay, thank you so much, Gopika. Thank you so much. You are liking it? Awesome. Let's go on. And I hope you guys are smashing the like button. In case you have forgotten, I need to keep reminding you every time. Smash the like button, smash the like button, smash the like button. Call your friends. What are they doing? Sleeping. Many of the students started preparation in the Avenger batch or wherever. Some students slept off. Some students are attending the classes regularly, and I'm seeing their names regularly in their chats or in the comments if you are watching it recorded. So keep that spirit up. I want to see all the students who are right now not awake, sleeping or lost or not confident in the classes every day. Be it physics, be it chemistry, be it biology, you should be there over here. Okay? Because we are committed towards our goal. We are not going back to chapter 1. We have already done chapter 1, 2, 3, whatever. Already we are midway. So it's your duty that you need to go back, because many people will come and tell you, I will start right from the beginning. I will start right from now. The time is gone. You have to go back, watch the recorded classes, follow, or else we'll be so behind. We'll not get enough time for revision, practice, mock tests. So please buckle up, please attend all the classes. If you have backlogs, make up your minds. Start again from chapter 1, sir. I will wait for that day you start again chapter 1. That is not going to happen. Don't wait for that day. Moving on to the next question. There is a coil of radius r carrying some current. Magnetic field due to the coil on the axis is how much if this distance is very large? Wow, what a question. So you have a coil and the distance is very large than the radius of the coil. So you are very far away as compared to this radius. Let's use the formula. I think it will be more of a formula based question. Thank you, Leo Mustab. Okay, so let's try to figure this out. Magnetic field will be mu naught I r square divided by 2 times r square plus x square raised to 3 by 2. Here x won't be x, here x will be small r, right, raised to 3 by 2. See, if r is much larger than r, what does it mean? If I do r plus r, won't it be approximately small r only? This is like 1000 meters versus 0.1 meter. 1000 plus 0.1, 1000 plus 0.1 is 1000 only. Same way, if I do r square plus r square, won't it be approximately r square only? Won't it be approximately r square only? So why not do that over here and see what happens next? Well, this will become mu naught I r square divided by 2. Forget this capital R because that capital R is very small as compared to this guy. So it will be just only small r square raised to 3 by 2. So this will become mu naught I r square divided by 2 raised to 2 raised to 3 by 2. 2 and 2 cancels, so it will be r raised to 3. Don't you see that the magnetic field is inversely proportional to the cube of the distance? So cube of the distance is right over here in option D, of course. Some of you already said it. Very good, Yuvan. Yes, Alekhya. Perfect. Yes, Priyanka. Very good, Subhash. Awesome, awesome, awesome. Let's move to the next question. Let's move to the next question coming up on your screen. Here it is. Find the magnetic field at that point. I think that point is right over here. That point is right over here due to the current carrying wire. It's straight from minus infinity to infinity, but a small part has a bend. You know what? Divide this entire geometry into 3 parts. This one, this arc, and this one. Each part will give some magnetic field. Find the magnetic field due to each one of them and just add them. Okay. If you look at this particular part, which is carrying some current, or even this particular part which is carrying some current, okay, believe me, it is on the axis of the wire. And I just told you, on the axis of a straight long wire, it will have zero magnetic field. So they have no contribution at all. They have no contribution at all in the total field. So might as well ignore them. So basically, I can just ignore the straight parts in this. Is that right? So the only thing which is there is the curved part. This curved part, this particular curved part is like an arc. Okay, it is carrying some current. There is some radius, let's say it is r. So the magnetic field due to that arc is mu naught I by 2 r. Here r is r. And here you have the fraction. What is that fraction going to be? Think about it. It's a semicircle, so it is basically half. If it's a quarter circle, it will be 1/4. This is a semicircle, so half of a coil will come over here. So hence it will be mu naught I divided by 2 2s are 4, 4r. So that is the magnetic field. That's it. That is the total magnetic field because there is no other contribution coming from anywhere else. So that is the answer. Understood? And because the current is going like this, the thumb comes out this way. So I think the magnetic field will be towards you. So that's how the magnetic field will be, towards you. Perfecto. Let's go to the next question coming up on your screen. You can see there are 2 arcs and 2 straight lines. Find the magnetic field again. Let's say the point P is given to be over here. You can assume the current to be I, radius to be R1 and R2. Okay, like we can make some assumptions. Now think about it. If I want to find the total magnetic field, I will divide it into 4 parts. This, the small arc, this straight wire and the big arc. Each will give some magnetic field. But out of these 4, I have a feeling 2 of them will not even contribute. Who are those 2? Again look at it properly. This one as well as this one, they will have no contribution whatsoever because it is on the axis. So you can completely ignore because it is on the axis. So no contribution in the total field. But this part and that part, yes, they will give rise to magnetic fields. So let's see each one of them. Like for example, I think this one. The current is going like this. The radius, let's say, is R1. This is the current. The magnetic field due to that Check this out. The current is going like this. Turn your fingers in the clockwise direction. The thumb goes inside. So the magnetic field must be inwards like this. So the magnetic field due to the first part, the first arc, will be mu naught I by 2r1 into half. Why into half? Because it's a semicircle. This half is only because it is a semicircle. That means it will be mu naught I divided by 4r1. Similarly, think due to this outer arc, the current goes like this, right? It has to come here, comes like this, then goes like that, comes back over here. That radius, let's say it is R2, the current is going exactly opposite. So the magnetic field will be towards me. So that magnetic field will be very similar to this mu naught I by 2r2 again into half, which will make it mu naught I by 4r2. Are these fields going to add or subtract? Are these fields going to add or are they going to subtract? So when I find the net field, understand both of them are opposite to each other. So very, very important, both of them are opposite to each other. So they will try to cancel each other, but obviously B1 is more than B2 because the smaller arc, small distance will make the B large. When R is small, B will be large. So it will be nothing but B1 minus B2, which is mu naught I by 4, and I have 1 by R1 minus 1 by R2. So that is the total magnetic field. Which direction will it be? It will be in the direction of the larger field. This is more, this is small. This is more, this is small. So where is B1? B1 was inside. So this magnetic field will also be in the inward direction. That's how I get it. Good evening, Niranjan. Everybody. Okay. I am not able to attend Avengers batch, so I'm not started. What to do? Gopika, I would say start with the one shots on YouTube. That will be better. That will be a time saver. Skip or watch it at a higher speed if possible. So that will be a best way to start. Do the 11th part first, then go to the 12th part. Follow the exact same flow as it is there in the Avenger batch. Same flow if you follow, you will cover up the portion faster. You will finish many things very soon. Right? So moving on to the next question coming up on your screen. This was asked in NEET 2019. Let's see how many of you can crack it. Current goes, distributes and comes over here. Question is find the magnetic field at the center. 0, this much out, this much in, this much in. Very interesting question. You can spend some time solving it. But I will give you a trick, not just for this, but for any question. Be it any question like this. Say there is a square. Okay, current comes like this, goes out like this. Or let's say it's a hexagon. Current comes in like this and goes out from here. Or let's say it's a circle. Current comes in like this. Current comes in like this and maybe it goes out from here. Doesn't matter, whatever it is, it could be a triangle also. Okay, let's say the current comes in like this and it goes out like that. Whenever such diagrams are there, remember one important thing. The current will get distributed. Some part here, some part here, some part here, some part here. Some of the part here, some of the part here, some of the part here, some of the part here. Each of these currents will create opposite magnetic fields. So you will always see that the magnetic field at the center, magnetic field at all these centers, magnetic field at all the geometrical centers will be 0 because they will cancel out each other. If you take any particular point, okay, if you take this particular point, due to this, if the field is in, due to the lower one, the field will be out. Due to the other one, the field will be basically out. So that's all. So that's how the field basically just cancels out. So you should remember this is true for every other polygon. Is that right? Everybody with me? Wow, we have some insect coming over here. Just 1 second, guys. Okay, chalo. ठीक है. So the correct answer for this particular question is just a big fat 0. Okay, keep this in mind. Is that right? It doesn't matter what the geometry is, as long as it's a regular polygon and you have some current which is coming in and the current which is going out, that's enough for the magnetic field to be 0. Clear? Okay, moving on to the next one coming up on your screen. This is now Ampere's law. We are going to see Ampere's law and the application of it, right? So what is this law? This law is like Gauss's law in electricity. Everybody knows Gauss's law in electricity. Everybody remembers Gauss's law in electricity. Same way, this is a Gauss law but for magnetism, which helps me find the magnetic field without actual integration. So imagine you have, let's say, certain wires, okay, which carry some current. Let's say this is one wire which carries some current, this is another wire which carries some current, this is another wire which carries some current. Let's say this is I1, let's say this is I2, let's say this is I3, and so on and so forth. You start from a point, maybe let's say over here, and you go in any random path, doesn't matter, and what you do is you have to come back. What is this? A path where you start from any point, you go anywhere randomly, and you come back to the same point. This is basically now a closed path. Do you see that? This is basically now a closed path. These currents I1, I2, I3 are piercing inside that path. Imagine that blue wire, that blue path. The currents are piercing through that particular closed path. So I1, I2, I3, etc. I1, I2, I3, etc. They are called as enclosed currents. What are they called? Enclosed currents. There might be some other currents also. Maybe it is going like this. Maybe this is capital I1. Maybe over here also. Maybe this is capital I2. This I1 and I2 are not piercing through that blue part. So this capital I1, capital I2, etc. they are basically outside currents. What are they? Outside currents. Now this I1 at, let's say, any point, let's say I take a point over here. At this point, this I1 will create some field. This I2 will create a field. This I3 will create a field. This I1 will also create a field. This I2 will also create a field. So there might be a net magnetic field. I will call it as B. So this B is the magnetic field, due to 1, 2, 3, which are basically internal or the enclosed inside currents, plus the magnetic field due to the outside currents, B1, B2. Remember, they are outside. Okay, so they are basically outside currents. Now at every point there will be a new value of magnetic field, because each wire carrying current creates its own magnetic field. Each wire carrying current will create its own magnetic field. Everybody agrees? Now you are going in that path. So let's say I cover a small distance. Let's say I cover a small distance and I call it DL. DL is the small distance along that closed path. Okay. I go at that point, I find the new field. I go at the next point, moving DL distance, I find the new field. I further go DL. At every point, I find the new magnetic fields. And what I do now is I take the dot product of that magnetic field with the distance that I travel, and I keep adding them. B dot DL, I go ahead, B dot DL dot plus B dot DL plus B dot DL plus B dot DL plus B dot DL plus B dot DL. I come back. I go across that, closed path exactly once. Meaning I have to just sit and integrate. But because I am coming back to the same point, this symbol is very important. What is that symbol representing? It is representing closed integral, closed path. That means you are coming back to the same point. Initial and final point is the same. That is the meaning of that. That is equal to that is equal to, just like in electrostatics, electric field into area vectors integration was enclosed charge by epsilon. Here it is enclosed current which is basically enclosed, not divided by but multiplied by permeability. So in magnetism and electricity, the formulas are always exactly opposite. If something is there in the numerator, it is there in the denominator in the other one, but they look very similar. So this is called as the Ampere's law. This is basically called as the Ampere's law. The closed line integral of the magnetic field, the closed line integral of the magnetic field is mu naught, permeability into the enclosed current. Permeability into the enclosed current. Is that right? Everybody with me? How to use it? Don't worry, I will tell you. Number one point, you will be thinking, what is the value of enclosed current over here, right? You all might be wondering, what is enclosed current over here? You'll be like, yes sir, I1, I2, I3, the small i's are the enclosed current, so it will be I1 plus I2 plus I3. Wrong, it is not I1 plus I2 plus I3. Some currents are positive, some currents are negative. How do I know which is positive, which is negative? Well, just look at the path. Just look at the path. How are you going? Like this, right? Just take your 4 fingers. You are going along the path like this. If you go along the path like this, the thumb goes upwards. So this becomes the positive direction. This becomes your positive direction. How did I get it? Using right hand thumb rule. That's all. Move along the path. The thumb goes in a particular direction. That is your positive direction. So I1 and I3 are positive. I2 is definitely negative. So hence this enclosed current will be I1 plus I3 but minus I2. That's how you get it. Is that right? So there is a sign convention in currents. A lot of people do not know. ABD, you are from Pune and you got 685. Whoa, which college are you going to go? That's crazy. Proud of you, my dear student. Amchi Pune rocks. Kamesh, hello. Yep. Is any modules enough to crack AIMS New Delhi? Trust me, the Unacademy modules, the notes which I am giving in Avenger batch and the books I have recommended in Avenger batch, that's more than enough to get into AIMS. You don't need any other book, Gopika. Okay? Is that right? Everyone with me? Shall we do some questions? Shall we do some more understanding problems? So let's see how to exactly apply Ampere's law. Imagine that there is a long wire. This is a long wire which carries some current. I want to find the magnetic field because of this. You'll be like, sir, I already know it. Hold on, I know you know it, but let's say I want to derive it. Remember, previously I did not do the derivation, I just told it comes via some integration. So now I will show you how exactly it comes, because it will be very simple to find it out using Ampere's law. Okay, it will be very simple to find it out using Ampere's law. So let's see how to do that. So I just know one thing, that the magnetic field lines are, circular. Okay, so I can just draw a random magnetic field line, maybe like this. Magnetic field line, let's say like this. This is your magnetic field. Okay, at every point the magnetic field is in the concentric circle, and maybe you can just take let's say this particular distance as r. Okay, this is r. Now why not take the path itself in the direction of the field? Always choose such a beautiful path where the integration vanishes, where the integration does not seem like integration. Just like in Gauss's law, you used to choose the areas parallel or perpendicular so that either the dot product is 0 or it is 1. So same way, either choose whether the path should be parallel or perpendicular. Why not go exactly along this path? Why not go exactly along this path? So this is my closed path, and I will go also just like this. I will go also exactly in the same direction. So this is my DL. This is my closed path. This is my closed path, sometimes also called as the Ampere's path, Amperian path, one and the same thing. If you notice, at every point the magnetic field is parallel to DL, parallel to DL, parallel to DL. Can I see that? B vector has been chosen in, DL vector has been chosen in such a way it is always parallel to it. So even if I do the dot product with DL, even if I do the dot product with dl, it will be b dl cos 0, which is just b dl. Think about it, which will be just b dl. B vector dot dl will be b dl cos 0. Cos 0 is just 1. That's all. There's that dot product which has just gone, vanished. Now let's use our Ampere's law, right? Let's use our Ampere's law. So as for that, cyclic integral b dot dl will be mu naught into I enclosed. This I already know is b dl. Very good. So it is just b dl, the vector sign goes. Mu naught, inside current there is only one current, and that is I. So just multiply it with I. For this particular path, only one of the current is piercing through it, so that current will come over here. This magnetic field is a constant, so put it outside. Just the integration of dl. You'll be like, sir, I have to integrate dl. How do I integrate dl? Use common sense. dl plus dl plus dl plus dl. What is that? Perimeter. Circle's perimeter, circumference. So that will be nothing but 2 pi r is nothing but mu naught I. So therefore B will be mu naught, 2 pi comes below, I is on the top, R also comes below. So that is the answer which we anyways knew. But this is the proof of it using Ampere's law. Is that right, everybody? Yep. Conquer batch, I don't know, bacha. It depends on your sincerity and your commitment. If you get demotivated very easily, then it will not be enough. Trust me. But if you need that motivation, if you need somebody to push you, obviously you will need that. You need those mock tests. You will need the Avenger batch. Many students are there probably who are already enrolled in coaching, but maybe they are not wanting to spend more money, or they want that free education. They want to learn from YouTube. So for them, this is the Conquer batch. You might be already enrolled. Maybe you do not have money, or whatever reason. You want to revise the topic. Okay, you might be enrolled in any offline or online coaching, doesn't matter. So that's why I am coming over here every day, so that every student is benefited. Students who are not joined coaching, who can enter a batch, you have the time, join the Avenger batch. You don't have time, you're already enrolled somewhere, you want to revise, or you want to learn from the scratch, you have the YouTube batches, which is the NEET Conquer batch. Cool. All right, now there is a modification to this. I will extend this slightly. I will play around with this now. A wire produces a magnetic field around it, but can a wire inside it create a magnetic field? Can a wire inside it itself create a magnetic field? Very interesting question. Think about it. Imagine this is my wire. Something like this. Imagine the wire is carrying current. Can the inside part itself have some magnetic field? That is the question that I am asking you. Okay, so this is now basically your R, and the current, okay, is going like this. Are you able to visualize this? There is current which is going throughout that. Is there a field inside it? The answer is yes. And again, the field line has to be symmetric. It has to be closed loop. So the only option for the field line is it has to be again circular. So there will be circular field inside as well. So let me show that to you. So there is definitely circular field over here also. Something like this, maybe. Well, not so great. Yeah, something like this. Okay, something like this. This is how the magnetic field lines will look like. Again, the direction given by the right hand rule. If you put the thumb in the direction of the current, the fingers curl, that will be the direction of the field. So the field will be basically like this. This is nothing but your magnetic field. Okay. How much is this magnetic field is the question. Okay. So very, very interesting one. So
I will basically, look at the cross-sectional view. That will be better. So imagine this is the cross-sectional view. This is basically the cross-sectional view, and remember, this is the radius, right, which we called it as R. I will take this particular magnetic field. Okay, this is that magnetic field, and this particular magnetic field, because the current is going inside, I think the magnetic field will go like that and come like this. This is how the magnetic field looks like. Okay, I will take a path, Amperian path, exactly around that magnetic field. I will take an Amperian path exactly with the magnetic field. So I'm going also like this only. I'm going also like this only. So that is my DL. That is my DL. And now again you can see magnetic field is always parallel to DL. So B dot DL will be B DL cos 0. So everywhere it is just B DL into 1, which is B DL. Everywhere along that Amperian path. Everybody with me? Everybody with me? Okay. Now let's apply our Ampere's loop law and see what happens. Cyclic integral B dot DL is equal to mu naught I enclosed. B dot DL is just B DL, and in the next step B comes outside, so it will be B cyclic integral DL. Now what is cyclic integral DL? DL plus DL plus DL plus DL. It's the perimeter of this. It's basically this perimeter, that DL that you see. If you keep on adding it, it's the perimeter. Okay, let's assume that this particular distance, okay, this particular distance is small r, the radius is small r. So this will be 2 pi small r, not capital R. A lot of people make a mistake over there. Okay, so that becomes my LHS. That becomes my LHS. But the problem is I want the value of the B. What is the value of B? I have to shift 2 pi r below. So you will be like, yeah, it is mu naught I by 2 pi r. No, it is not that. Reason is this I enclosed is no longer I. That is the catch. See, current is going in. Not the entire current is I enclosed. Some of the currents are inside of it. Some of the currents are definitely inside of it. But don't you see, some of the currents are missing that loop. Some of the currents are definitely missing that loop right over here. Do you see that? Some of the currents are outside. So the enclosed current is only in this much part. How do I find that? Well, that's simple. Think like this. Total current I was on that complete area, which is basically pi r square. So in that enclosed part, how much will be that current? It will be only in this much part. What is that area? Pi small r square. Current per unit area will be same, right? Whether I take this part, that part, whole part, small part, current per unit area will be same. Total current was on pi r square. This current was on pi small r square. So can I not say I enclosed by I will be pi small r square by pi capital R square? Both pi cancel, so I enclosed should be small r square by capital R square into I. Is that right? Everybody with me? Everybody with me? Understood? Clear? Perfecto? Yes, you have regular classes only, Dhanalakshmi, because that's how I am. And you see, every day there are classes, but yeah, don't expect everyday physics, everyday chemistry, everyday biology. Okay, so they will have to take turns because we also have batches. I am also on the JE channel, so I hope you understand. But let me promise you that I'll be completing your entire 12th standard syllabus. Don't worry, on YouTube. Okay, in the next few months. By October, it will be done. Don't worry about it, Dhanalakshmi. Okay, and all others. Okay, so just substitute that. So that is nothing but mu naught into I enclosed, which is I into r square by r square. Okay, I think one of the r just gets cancelled right over here. So B will be mu naught I by 2 pi capital R square into small r. Very interesting formula. It's slightly different than the previous formula. Instead of mu naught I by 2 pi r, It is mu naught I by 2 pi r square. So because it is r square, you put an r on the top, but that is small r. So this is the formula. You know what I should do now? I should combine this formula with this formula. This was already studied before. This was already studied before. We can combine these two formulas into one single formula or one single, slide. And I can just say, if I have a wire of some radius r carrying some current, so the current is like this. If I am inside the wire and the distance is small r, the magnetic field lines will be again circular like this. That magnetic field inside will be mu naught I small r by 2 pi capital R square. This is when r is less than r. But the moment you go outside, basically like this, then the field at that distance of r, then the magnetic field outside at that distance is just given by mu naught I by 2 pi small r. This is when r is more than r. So you can now see it's in a combined form, it's in one single slide. You can also look at it graphically. If this is the distance, if this is the field, how should it look like? When you are inside, it is directly proportional to r. That means it must be a straight line. It should be a straight line till r. But immediately after that, it is inversely proportional to r. So it must be like this. It will be a curved line. Perfect. Gopika, I don't think so. I think the Avenger batch entry is closed as of now. Yep, it's closed. Okay. Is that clear? Understood? This is very, very important slide. Very, very important slide. Star market, very important graph, very important theory, derivation. Everything I've done properly. I've not missed any step. Okay. So whatever I have done over here, make sure you understand it. I have started with Ampere's law. I've told you how to apply Ampere's law. We have taken two examples on it for field outside the wire and field inside the wire. I showed you the combined result as well as the combined graph. Cool? Very good. I hope you are subscribing to the channel. In case you haven't done that yet, please do that, or else you'll miss the classes, and smash the like button in case you have forgotten. Cool? Chalo, let's see the questions coming out on Ampere's law. The field on the LHS is due to dash and the closed line integral is due to dash. I think the blank is missing, but I'm asking you the question. The LHS of the Ampere's law equation. So what is the LHS of the Ampere's law equation? It is this: cyclic integral B dot dl is equal to mu naught I enclosed. So the LHS, come on, this part, the LHS, what does it depend on? The LHS depends on the RHS, obviously, and the RHS has only I enclosed. So it only depends on the enclosed, the total value, but the field in it, they are asking what is the field dependent on, field on the LHS. So on the LHS, if you notice this particular field, I just told you it is because of both in and out, both the inner as well as the outer currents. So in this case, it is I1, 2, basically the last current, whatever is there, I think it is I6. All the currents in and out, all of them are going to be involved for finding the value of B. But the integral value, the complete integration, this entire integration's value is just dependent on this, is just dependent on the enclosed currents. So enclosed currents are just I1, I3 and I5. So that is the answer for the second part of the question. So the second part, the integration value, the complete value of the integration depends only on the enclosed currents, but the inside value depends on both inside and outside currents. Is that right? So that is the catch in this particular question. Many students think both of them are because of enclosed, but that is wrong. Similar question was there in electrostatics also. Let's see if you can solve this. Imagine a current is flowing along the pipe, then the magnetic field is 0 on the axis, magnetic field is different, magnetic field at any point is 0, magnetic field at all points is non-zero, I think. That word is missing, non-zero. Okay, so think about it. What must be the answer? There is a pipe. There is a pipe. Just imagine this is the pipe. It is carrying currents like this. It's carrying currents like this. So question is, what is the magnetic field inside that particular pipe? If you take any point inside that particular pipe and if you draw an Amperian loop, if you draw an Amperian loop or a path, it's a closed path. Remember, the currents are only over here. The currents are only on the thin walled pipe. It's not a solid like before. If you notice, there is nothing to be enclosed. There is no enclosed current only. What is the current which is enclosed? There is no enclosed current. There is no enclosed current. If there is no enclosed current, obviously the RHS will be 0. That means LHS will be 0. That means magnetic field will be 0 everywhere. Everywhere. Doesn't matter how big is this path, as long as it is inside, everywhere the field will be 0. So hence answer is C. Hence the answer is C, like you can see over here. Is that right? No, it is not A. Okay, is that right? Great, great. Gopika will try to open up the Avenger batch. Maybe we'll have a separate entry point in the days to come. So till that time, continue watching the YouTube lectures. Okay, great. Hello Hariharan, nice to see you, Bacha. Nice to see you. And you can also let me know since how long you have been watching and following this channel or me. I'll be very happy to know that. Yep, moving on to the next question. A long wire of radius A carries some current. Current is uniformly distributed. Ratio of the field at half the distance of the radius and twice the distance of the radius is how much? Okay, simple. When you are at A by 2, basically you are inside. So the magnetic field in the first case will be mu naught I by 2 pi radius square, that means A square, into the distance, which is basically A by 2. So which comes out to be mu naught I A cancels actually. One of the A cancels. 2 into 2 is 4. So 4 pi A. So that is the magnetic field at the point A by 2 from the center. You are using mu naught I R by 2 pi R square because inside the formula is different. But the moment you say 2A is more than A, remember I just told you there are two formulas, inside and outside. When it is less, when it is more, inside and outside. The formulas only are different. So when you are basically outside, the magnetic field will be mu naught I by 2 pi R. R over here is 2A. So which is mu naught I by 4 pi A. Interesting thing to note is B1 and B2 both values are same. So B1 by B2 will be 1:1. So 1:1 means 1. Option C is the correct answer. Is that right? Everybody with me? Perfecto. Great. Moving on to the next question coming up on your screen. Solenoid and okay, so for that we need to study the solenoid and the toroid. So you have seen the basic applications of Ampere's law, right? We just seen the basic applications of Ampere's law. Now let's go to something called as the solenoid and the toroid, which are the secondary applications of Ampere's law. What is a solenoid? What is a toroid? Simply put, if you take a coil and the next turn is beside it, something like basically a helix or a spring, that coil, if now it carries some current, that is basically called as a solenoid. You would have seen, you take a nail and you wind copper wire on it, it becomes an electromagnet when you pass current. So that is basically a solenoid, a coil carrying current, but the coils planes are different, parallel to each other, like a spring or a helix adjacent to each other. The magnetic field due to that will somewhat be like this. This is how the magnetic field looks like. They travel inside also, and they will again come out from here. So that's how the magnetic field lines are. But a toroid is very similar to a solenoid, just that you
you bend the solenoid and do not keep open ends. You have the left end and the right end of a solenoid. You don't keep those ends. You bend it and join them. So it looks something like this. So this is nothing but a toroid, and in this case the magnetic field lines are just stuck inside of it. This is how the magnetic field lines look like for a toroid. So this is a toroid, which is nothing but a bent solenoid, nothing else. It's a bent solenoid. Is that right? Thank you so much. I'm so glad that you are loving physics, and I'm pretty sure this relationship will go on till you crack NEET and till you get your college. Nice to see students dedicated and following physics like you. Thank you so much. So, how much is the field inside the solenoid and the toroid? That's what we want to find. And basically, the derivation goes something like this. If you take a solenoid, oops, let me just show it like this then. There are many windings over it, something like this, correct? Okay. You will see that the magnetic field will travel from inside also. This is how the magnetic field lines will look like. Some of the field lines will go like this, come over here. Some of the field lines will go over here. The other field lines are going to go really far away. Think about it. They are going to go really far away. So the most important thing about a solenoid that you should know is that once you are outside, the field lines are so far away, so sparse. Instead of dense, it is sparse. That means very far away. The magnetic field outside is just negligible. How much is it? Just negligible. Is that right? Everybody with me? Next important thing. If you notice the magnetic field lines inside, after reaching inside, they just look something like this. After reaching inside, they probably look something like this. Do you see the field lines are roughly parallel here? Do you see the field lines are roughly parallel over here? Exactly. So in this region, you will see magnetic field inside is uniform. What is it? Uniform. Keep this in mind. Magnetic field inside the solenoid, because the lines are parallel, it is roughly uniform in nature. That's the next observation that you can do. Third observation. Here the field lines are parallel, but you will see as they come towards the end, they go slightly far away. As they go towards the end, it is slightly far away. So although in this region it is uniform, when you reach the end, slightly the distances have increased, so the field has reduced slightly. So that brings me to the next point. Magnetic field at the end is slightly less than the magnetic field at the center or near the center, which is almost uniform. Make sense? Everybody with me? Now, what are the parameters that are generally given to you? I is the current. I is basically the current which is flowing in the solenoid. The next thing that will be given to you is small n, which is the number of turns per unit length. That is basically the total turns per unit length of the solenoid. Meaning if you take 1 meter, how many windings are there? 300, 200, 100, 20, whatever that could be. That is the meaning of small n. That's the number of turns per unit length. Keep this in mind. Then outside, though I know it is 0. Inside, the magnetic field is just given by mu naught small n I. That's it. This is the formula for the magnetic field inside the solenoid, which is uniform. But if you go to the end,
the magnetic field formula is very similar, just that in fact it is half of it. So by 2. At both the ends it is just by 2. This is the formula which you should know for a solenoid. At the center it is uniform, it is mu naught Ni, number of turns per unit length into permeability into current. But at the ends, both left and right, the field slightly weakens, it becomes half the field at the center. As simple as that. Right? So Gokul, welcome, Bacha. Everybody else, I hope you guys have noted this down. Now we can also look at toroid. We can also look at basically toroid. Maybe I can just draw 2 circles first. Okay, so this is your toroid. Now usually this is called as the radius of the toroid. This is called as the radius of the toroid. This is thin. Imagine this is 100 centimeters, this will be 102 centimeters. So this width is very small, and the windings are obviously like this. The windings are like that. So there will be magnetic fields inside of it. How will the magnetic field lines look like? Let's have a look at it. Something like this. Yeah, this is how the magnetic field lines will look like, and the windings, like I told you before, it will be something like this. That will be the tube of the toroid. That will be the tube of the toroid. Toroid is nothing but a solenoid only, but I have bent it. I've just not allowed the field lines to go outside. I just take it and bend it. Just look at this. The same solenoid, I bend it, and I, merge them together. So I will just get a toroid over here. I hope everybody is able to visualize this. Right? Now the formula for toroid should be exactly same as a solenoid, because it's a solenoid only which is bent. Okay. So first things first, outside there is no magnetic field, so it is just 0. The inside magnetic field will be just like the solenoid. Just like the solenoid, there is no difference. So it will be mu naught small n I. That's it. It's the same formula for a toroid. So toroid and solenoid both have same formula, because it's just the same thing. You bend it, that's it. That becomes your toroid. So this was for a solenoid. But keep in mind over here, what is that n going to stand for? Number of turns per unit length. Here the length of the toroid will be 2 pi r. Will be basically 2 pi r. That would be the length of the toroid. So formula wise, it is exactly the same. There is no difference. Just that you should keep in mind what is the value of n, right? So I'm just blocking it over here. Number of turns per unit length. The length of the toroid. The length of the toroid will be the circumference, which is 2 pi r. That's all. Yep. Right? Let's go ahead. Let's solve some questions now. So we have done solenoid, and we have seen how the field lines look like, and we have also seen how does it look like for a toroid. So let's have a look at some questions. Here is the first question. There is a solenoid by 20 turns per centimeter. Current necessary to produce a field of 20 millitesla will be approximately how much? Will be approximately how much? Come on, my dear students, use the formula properly. Which formula will you use? It's a solenoid, so the magnetic field is given by mu naught, number of turns per unit length, into current. Question says field is 20 millitesla, so 20 into 10 to the power minus 3 is B. Mu naught I already know is 4 pi into 10 to the power minus 7. Number of turns is 20 per centimeter, so if 20 turns are there per centimeter, think about it, it will be 20 per centimeter. 1 centimeter is 0.01, so it will be 20 into 100 turns per meter. per meter, right? So I'll have to put over here number of turns as 20 into 100, and lastly I have to find the current. Now it's just a matter of calculations, there is nothing great about it. So cancel this 20, cancel this 20, and shift the values. So current will be 100. If I take it here, it will become 10 to the power minus 2. With this minus 3 will become 10 to the power minus 5. This will become 10 to the power minus 7 below, and into 1 by 4 pi. Come on, so this will become basically 10 to the power 2, which is basically 100 divided by 4 pi. So this goes with this 25 times. So 25 by pi. So basically 25 by 3.14. 24 by 3 is 8. So it will be close to 8 amperes. So question itself said approximately. So it will be 8 amperes. So let's check it out. Yes, it is almost 8 amperes. There we go. Is that right? Is that right? Everybody with me? Yes. Thank you, Rakesh, for promoting Unacademy also. है ना? So it seems like the PW students over there have no other job but to come over here and spam. Maybe that's how you are increasing your viewership. है ना? Who knows? All right. Moving on to the next question coming up on your screen. I don't see my students doing that anytime. So go study, don't waste your time. If you want to study from anywhere, go and study over there. Don't waste others' times and don't spam like this. It shows how cheap you are. A long solenoid has some length, has some turns, has some current. The magnetic field at the center is NEET 20 question, direct question. Direct question was asked. Imagine mu naught Ni, that's all. Mu naught is 4 pi 10 to the power minus 7. Number of turns 100, but for 50 centimeters, so per 0.5 meters, so divided by 0.5. That division by 0.5 is important. Turns per unit length, length is 0.5 meters. Okay, into the current. How much is the current? 2.5. 2.5. That's it. So check this out. This will become 4 pi into 10 to the power minus 5. And this 0.5 also, if you want to take it up, okay, this will become into 10, and this is basically 2.5 divided by 5. 10 goes with 2.5 becomes 25. 5 goes with 25 becomes 5. 5 4s are 20. So 20 pi into 10 to the power minus 5. So this will become 2 pi into 10 to the power minus 4. 2 pi means 6.28 into 10 to the power minus 4. 6.28 into 10 to the power minus 4. That is option C. Exactly. There you go. Option C. Great. Very good. Very good. Very good. Awesome. Many of you would have cracked this NEET 2020 Corona paper 100%. Such a simple question came. This was asked in NEET 2019. Wow. Two toroids have turns 200 and 100. Average radius 40 and 20. They carry the same current. What is the ratio of the fields inside those toroids? Direct formula of toroid, nothing great. Direct formula of toroid is mu naught, number of turns by 2 pi r, turns per unit length, into the current. So B1 by B2 will be N1 by N2 into R2 by R1, because it is inversely proportional to R. So what is N1 and what is N2? 200 and 100. So 200 and 100. What is R2 and R1? 20 and 40. So this is 20 and this is 40. Obviously this is 2, obviously this is half, so it will be 1. So 1:1 is the answer, which is A for apple, A for Ames. Perfecto. Very straightforward question. Telugu, my Avenger batch is closed as of now. When it opens, I will let you know. Okay, so the entry points are closed. Moving to the next question. Long solenoid having 800 turns per unit length, okay, current is this much, magnetic field at the end of the solenoid, be careful, end. So magnetic field at the end of the solenoid is mu naught Ni by 2, that's all. So substitute, mu naught is 4 pi 10 to the power minus 7, number of turns 800, current 1.6, whole thing divided by 2, whole thing divided by 2, that's all guys. So just do the math and see how much do you get. Let's do the math and see how much do you get. This 2 goes with this 4, becomes 2. 2 into 8 will become 16, and you have pi, and you have 10 to the power minus 7. Okay, 2 into 8, 16. So those two zeros are there, and take 1 0 over there maybe. So maybe I'll just put 10 into 16. I just shifted that decimal by removing 1 0. Okay, so this will become 16 into 16, 256 pi into 10 to the power minus 6. So 256 pi. So 256 into 3, think about it, will be close to 750. Slightly more than that, because 253s are 750. So 256 into 3.14 will be close to 800. So it will be something like almost approximately 800 into 10 to the power minus 6, which is then 8 into 10 to the power minus 4 Tesla. 8 into minus 4 Tesla. Yes, there you go. That's the option number B. Is that right? Everybody with me? Perfect, perfect. Yep, option B is the correct answer. Very good, Pravina, Alekhya, Vidanjani, Priyanka. Very nice, very nice. Awesome. Moving on to the next concept, and this is the last concept of this chapter. And after this, the chapter comes to an end. We have completed almost everything that is needed. And trust me, we will have many practice sessions after the syllabus is over. I need your support in attending the classes. So, force between wires which carry current. We know a wire carrying current can produce a magnetic field. We also know a magnetic field acting on a wire can create a force. So can two wires besides each other carrying currents, two wires besides each other carrying some currents, apply force on each other? Answer is yes. So this wire will create its field which passes through the other wire which applies the force, and vice versa. This wire's field will apply a force on this wire's field will apply a force on this. So that's how they interact with each other. If you take the example of two wires which are basically carrying currents in the parallel direction, let's say this is I2 and let's say this is basically I1. This I1, if you hold your thumb in the direction of the current, the curled fingers will be like this. The curled fingers will be like this, like this. So the field will definitely go like that. This is how the magnetic field will go. Because of this wire, I'll call it as B1. Now this field will apply a force on this wire using the formula IL cross B. That is the force ILB. ILB. L is there, B is down. You can see the force is directed this way. So there must be a force like this. Same logic, if I apply over here, I will get a force like this. This force is basically attractive. So it is attractive when currents are in the same direction. Currents are in same direction. That's when it is attractive. Obviously, it will be repulsive if the currents are in the opposite direction. You can check it out. Imagine there is a current I1 and the current I2 is exactly opposite. Still, this wire will create its own magnetic field like this. So the field will be going like that over here, B1. Now you can see L is here, B is down. L is there, B is down. So the thumb goes this way. So definitely the force will be like that, like this. So this force is repulsive when currents are opposite. How to remember it? I told you electricity and magnetism are opposite but also similar. If something is there on the top, it is there below. If something is there below, it is on the top. Formulas look very similar. In electricity, two like charges, positive, minus, will repel, right? In magnetism, two similar currents will not repel, they will attract. So two similar currents will attract. In electricity, positive, positive will attract. But in magnetism, opposite currents will repel each other. So that's how you can remember it. It's so simple. Okay, cool, great. How much is this force? We can easily find. If this wire has current I1 and if this particular wire has current I2, the force between them, whether it is same direction or opposite direction, does not matter. I'm interested in the magnitude. Can be found by first finding the field because of this wire I1, and that field will be nothing but mu naught I by 2 pi. Okay, let's assume some distance between them. Let's assume some distance between them. Let's say the distance between them is d. Obviously, any wire which carries that current at that distance d will create a field given by mu naught I by 2 pi d. Mu naught I by 2 pi d, right? So what is the force now? What is that force on that wire? It will be I, but I is of this wire, so I2 into length of that wire into the field on it, which is B1. So it will be I2 L B1. B1 is nothing but mu naught I1 by 2 pi d. Shift L below. So force per unit length will be mu naught I1 I2 by 2 pi d. This is a very important formula, will be helpful for solving problems. The force acting per unit length is mu naught I1 I2 by 2 pi d. Keep this formula in mind. Keep this formula also in mind. Okay, everybody with me? So mu naught I1 I2 by 2 pi d is the force per unit length. In fact, this is also the formula used for defining the unit of ampere. Like you can take mu naught by 2 pi as or mu naught as 4 pi by 10 to the power minus 7. If you place the separation as so many meters, then this is the force. Then the current passing is 1 ampere. So that's how unit of ampere is defined using this formula. Okay, using this formula. Cool. So you should know the directions, you should also know the magnitude. So I think we can solve some questions. First question on your screen. Two long wires separated by some distance carry current I1 and I2 in the same direction. They exert a force F. Now the current in one of them is increased to 2 times and the direction is reversed. Distance is increased to 3d. What is the new value of the force? First things first, if you read the question carefully, the direction is reversed. That means negative. Whatever is the force will become opposite. If it was out, it will come in. If it was in, it will go out. So answer should be negative. So it can't be B. It has to be either this, this or this. It has to be negative answer. Okay. Next step. The force acting per unit length is mu naught I1 I2 divided by 2 pi d. Notice what have you done? You have increased one of the current 2 times. So you have multiplied the numerator 2 times. The distance has been increased to 3 times. So won't this as a whole increase by 2 by 3 times? Won't it become 2/3 times? So 2/3, where is 2/3? Only in option C. That's the correct answer. Perfect. 2/3 but with a negative sign. So that is the answer. Simple. If you know the formula, you can do it like this. Moving on, next question. A current carrying straight wire is kept along the axis of a coil, of a loop. Then, will that wire exert an inward force on the loop, will exert outward force on the loop, will not exert any force on the loop, will exert a force on the loop parallel to itself? Interesting question. Imagine this is your loop and you have a wire which is like this, which carries some current. The loop is carrying some current. That will create its own field. And there is another wire which carries some another current, let's say I prime. So think about it. Will there be any force? How will the force be? Outward, inward, etc. Come on. Come on, my dear students. Well, due to a coil, I have just told you how the field looks like. Due to a coil, well, the field basically just looks like this. This is how the field looks like. Correct? This is how the field looks like. Oh, wait a minute. If I try to find the force using I, L, cross B formula, problem will be L cross B will be a big fat 0. You know why? Because length and magnetic field are in opposite directions or in the same directions depending on how you take the current. So L cross B will be 0. Is that right? Everybody with me? So basically how much will be the force? No force. So option will be C. There will be no force on that loop. So the loop will not exert force, nor will this exert any force. So the idea was, if you know the direction of the field, in this cross product, L cross B will be 0 because they are parallel to each other. Sine 0, sine 180, all of them are 0. Keep this in mind. Next question on your screen now. Okay, beautiful question. Observe. Consider the situation as shown. Straight wire is fixed, but the loop can move. It can go up, down, rotate, whatever it wants to do. What do you think will it do because of this guy's, because of this person's current's field? Think logically. Think logically. Okay? Observe. I think you have to consider each part of that loop. Consider each part of the loop. If you take this part of the loop, the currents are in the same direction. Same direction means attract. So there will be an attractive force. There will be an attractive force on this part. The current goes like this, it goes like that. When the current goes like this, the currents are opposite currents. This current, white one and the orange one, opposite means it will repel. But will this repulsion be same as the attraction? Will the repulsion be same as the attraction? Think logically. As you go far and far away, won't the field reduce? Here at this distance, whatever B1 you get, and at this distance, whatever B2 you get, will be different. In fact, it will become less. It will become weak over here. Is that right? If it becomes weak, won't this force also become weak? Because force is ILB. B will become weak, force will become weak. Yes, I know some disturbing sound is coming. I just saw outside there is some construction going on. I am so sorry, but I cannot do anything. Okay, so ignore it. Anyways, last 1 or 2 questions only are remaining. Okay, so this force is less. So where will be the net force? Where will be the net force? Come on, right side or left side? Obviously towards the left side. So won't the net force be towards the left side? Net force be towards the left side. You might be wondering, what about the parts on the top and below? Think, how will the magnetic field look like? Due to this current, the magnetic field will be, let's say, inwards, like this. Magnetic field will be inwards. Length is like that. IL cross B, length is like that. B is inside. So if you do the math, this force will come here. If you do the math here, the force will come exactly opposite because the current is going opposite. So IL cross B, force up, IL cross B, force will be down. So now what this means is that these forces will cancel each other. These forces will definitely cancel each other. So they have no role to play because they are at the same distance. Both are symmetric. So the only force applied is this one. There is no rotation, also no torque. All the forces are along the same line, so they cannot even create torque. So basically it will move towards the wire. It will just move towards the wire. The net force will pull it. That's all. Exactly. Moving on to the next question. 2 wires carry currents 20, 40 opposite. Another wire carrying current anti-parallel to 20 is placed midway. The magnetic force on it will be towards which of the wire? Beautiful question. Let's draw it. 2 parallel wires carrying currents in the opposite direction. So imagine this is 20 amperes and this is basically 40 amperes. What you have done is you are placing another wire carrying some current anti-parallel to 20 amperes. That means basically like this. There is some wire over here. What will be the force on that particular wire in between? Think logically. This wire and this wire are carrying opposite currents. Opposite means repel. So obviously 20 amperes current will create a repulsive force. There will be a repulsion between them. 40 amperes and I amperes are in the same direction. Same means attract. So definitely there will be attraction because of the 40 amperes. Obviously both are in the same direction, so net force will 100% be towards the right side. So where will the net force on the current be? Towards the 40 amperes. That's the correct answer, which is option B. So very logical question. If you know the directions properly, you will get it. Very good. Let's go to the next question coming up on your screen. This was a NEET 2017 question. Observe. There are 3 wires placed perpendicular. This is not a wire, this is not a wire. The wire is coming out of the plane. Visualize it. One wire here, one wire below it, one wire side. That white lines are the distance between the wires. The magnitude of the force per unit length on the middle wire B is how much? Because the currents are in the same direction, same means repel or attract? Obviously attract. So B and C wire will attract each other. B and C wire will attract each other. A and B are also carrying currents in the same direction, so they will also attract. So there will be an attraction like this. This current, this current, this current, this distance is same. So if this is F, obviously this is F. If this is force per unit length, this is also same force per unit length. So how much will that force per unit length be, by the way? That will be mu naught I divided by 2 pi d. D is d. So it is basically mu naught I square by 2 pi d. The forces are perpendicular. So guess where the net force must be? Obviously it must be here. So the net force must be root of this square plus this square, which becomes root 2 times of F by L. Correct? X square plus y square. Both x and y are same. X and y are same. So that's it. It will be root 2 times of that. So it will be root 2 times of this. So mu naught I square by 2 pi d. If you want to bring root 2 down also, you can do that, which is option B. Yep, root 2 and root 2 cancels, so root 2 will remain. That's the correct answer. So this kind of question has come in NEET 2017. So this is how they play around with the questions. I've kept some homework questions for all of you. Okay, so this is your first homework question. Please take a screenshot, solve it, post the answers in the comment section. All right, so then you have this particular question. Okay, solve this, take a screenshot, post the answers in the comment section. And then you have this particular question. All these are very straightforward questions. You will be able to solve it immediately after the class. This will build confidence. And one more question for all of you. Yes, there it is. So try to solve all these questions. They are straightforward. Answers will be there in the PDF, which I will upload in the Telegram channel. If you have not yet joined the Telegram channel, make sure you join it as soon as possible. I'll be sharing you the PDFs immediately after the session, right? So I hope you are enjoying the Conquer series, and if you are part of the Energize batch, I'm very proud of you. And don't worry, there will be an entry point soon. We'll try to do something for you. Right now the batch is closed, but keep watching all the classes over here. Okay, I hope you have smashed the like button. I hope you have hit the subscribe button as well. I hope you enjoyed, learned a lot, and practice via the homework questions and the books that I have asked you. If you have not yet watched the video, watch it. It's there. Just search for Shreyas Sir NEET books. You will get it. Okay, cool. Done. Bye bye Pravina, bye bye Priyanka, bye bye Alekhya, bye bye Joshi, bye bye Kenu, bye bye. Take care Vedanjani, bye bye. Have a lovely evening. See you again very soon.